Hello, my name is Zoralei Boysen, and today I'm going to be walking you through Ohm's law. Ohm's law states that voltage is equal to current times resistance. Let's take a look at each one of these variables individually. Voltage is the electric potential between 2 points. It is what causes the charges to move, the push force, if you will. Current is a term that most of us are familiar with. When we go to the river, there's a current, and water is flowing. With electric current, it's the same idea, except it's electric charge that is flowing past a certain point as a function of time. Resistance is another term that most of us are familiar with. We know that to resist is to push against or try to stop. In this case, electric resistance is the amount that a conductor resists the flow of charge. Okay, so we've already talked about how a river analogy relates to current. Let's take that a little bit deeper and look at how it relates to every variable in our equation. So here we have a river. This is where the river begins, and here's the ocean. The water in the river is representative of the charges that are flowing. The banks are going to be our conductor, and in turn, our resistor, as we talked about how they related. And our voltage is the difference in water between the beginning of the river and the ocean. The water in the river wants to get to the ocean where there's more room. As we discussed, our current is going to be the speed of the flow of water. So let's look at another situation. What would happen if we took the same amount of water in the same beginning of the river, but then we brought the banks closer together? This would increase the resistance. But we have the same voltage because we started out with the same amount of water that has to get through. So what would happen to our current? Well, as we can see here, this water is trying to get through this small area, so not as much water can flow through at a time. This would increase the pressure there, but it would decrease the current there, since not as many charges can move through this area. So if we look at our equation over here, if our voltage stays the same, but our resistance increases, our current is going to have to decrease to make sure that our equation works. Okay, so now we're in my backyard and we're going to talk a little bit more about how Ohm's law applies to each of us. Ohm's law is voltage is equal to current times resistance. Again, voltage is the change in electric potential, current is the flow of the charge, and resistance is the amount of resistance it has to overcome. Now, I'm an exercise science major, and we talk a lot about physiology. And an important concept in physiology is the circulatory system, obviously. It's so important in getting nutrients where it needs to go and getting rid of waste. So, one thing I learned in my physiology classes is that change in pressure is equal to blood flow times the resistance of the blood vessels. Now, if we look at these two rules, they are essentially the same. So we're going to talk a little bit about our circulatory system to help better understand Ohm's law. Now, in our blood vessels, the thing that we change most to change blood flow is the diameter of our blood vessels through vasoconstriction and dilation. There's a lot of reasons blood vessels can also change. For example, just like capillaries versus arteries and stuff like that. One thing that we need to watch out for, though, is atherosclerosis. This is a hardening or thickening of a blood vessel wall due to plaque buildup. Just eating right and exercising can help reduce this and make sure that we don't have this to keep our blood flowing as fast as it needs to and keep us healthy. One fun fact is that if we took all the blood vessels in our body and lined them up nose to nose, so in just one big line, it would reach over 60,000 miles. That's amazing. You're amazing. God is amazing. So through all this, the thing I've most learned about physics in the circulatory system is that the circulatory system is a circuit. It's super cool, and it follows Ohm's law. So we're going to talk a little bit about this experiment I've set up so that we can better understand Ohm's law in our circulatory system. Hope you enjoy. All right, so today this is going to be our experiment. We're going to pour water into these cups, and it's going to go down these tubes. We're going to measure the time it takes for the water to get from here to here. The time it takes is going to help us determine the velocity of the water, which we're going to take as our blood flow or current. The amount of water is going to stay consistent. We're going to fill these blenders to be just at 5 cups, and then we are going to pour them at a consistent rate. And this is going to make our change in pressure or our voltage consistent between both of them. The only thing we're changing is the resistance, and we're doing that by the diameter of these tubes. This tube is thicker at 1.5 centimeters, and this diameter is going to be 0.75 centimeters. So the smaller the diameter, the greater the resistance. We're going to then determine if we can put this kind of makeshift circulatory system into Ohm's law and show, kind of prove that it works. Everything else is consistent. They're both 6.5 feet off of the ground. They're both 178.4 centimeters long. So let's get to it and see how this works. We're going to do our first one now. Esmeralda's going to pour it into number 1 when I say go. Ready, get set, go. All right, so Esmeralda, gravity, and this cup are kind of acting as the heart. They're pumping blood to the rest of the body, which we kind of is similar. Stop. All right, we're at 21 seconds. Perfect. Now we're gonna do the next one. Ready, get set, go. Which is, so if we're talking about our electric analogy, the heart is very similar to the battery. This would be the conductor, and again, the liquid you're pouring is kind of equivalent to that voltage, that causing of the change in pressure. As you can see, she's trying really hard to pour it at a very consistent rate with the last one. And we are done. That took 29 seconds, significantly more. Now let's go to the whiteboard again and see if our results match what we said about our equation. All right, so let's look over some of these results to see how they work in our equation. So we have, for our first one, it had a larger diameter. It took 21 seconds for 5 cups to go through. This means that its speed is 0.2381 cups per second. For our second one, it took 29 seconds for 5 cups to go through. That means the speed is 0.1724 cups per second. As we can see, as we increased the resistance or decreased the diameter, but kept the same voltage or same amount of blood running through the tube, our current decreased. This is makes a lot of sense with our electricity too. We talked about how they kind of affect each other. So remember, stay healthy, keep your circulatory systems going strong. We're gonna head back into the classroom to do some equations now. So in your circuit, 20 coulombs go through a resistor, which is 4 ohms, every 5 seconds. What voltage must be being supplied to the circuit? So first, we're looking for voltage. So to find voltage, we need current and resistance. Well, we have resistance, so we just need current. And if we recall from the beginning of this lecture, we know that current, or I, is measured in amperes or coulombs per second. So our I will be equal to 20 coulombs per 5 seconds, or 4 amperes. Then we can just put this into our handy dandy Ohm's law and say that 4 amperes times 4 ohms is going to be equal to 16 volts. So that concludes our discussion of Ohm's law today. It's pretty simple. Just always remember that V equals I times R. Voltage is equal to current times resistance. Good luck.